This video summarizes how we can depict the motion of an object with pictorial models. There are many ways to model the motion of an object that would indicate its speed, direction, and any changes to its speed. Some students model the motion of a toy car by drawing cars and putting whoosh marks behind the car. The more whoosh marks behind the car, the faster it's going. So in our first row we see a series of drawings where we start out with 1, then 2, then 3 whoosh marks. This would imply the car is moving to the left and speeding up. On our next row there's 1 whoosh mark behind each car. This would imply moving to the left at a constant speed. Our final drawing shows 3 whoosh marks, then 2, then 1, which would be moving to the left and slowing down. If the car had been moving to the right, the whoosh marks would be on the left side of the car. Some students model the motion of the toy car by drawing cars and putting arrows in front of the car to show direction and speed. Some students say that longer arrows imply faster speeds. That would imply that the length of the arrow is the distance the car traveled in equal times. However, if the longer arrow implies a slower speed, that would mean that the length of the arrow represents the time that it was taken for the car to travel those distances. In our first row, we see depictions of 3 cars with arrows of equal length. This implies the car is moving to the right at a constant speed. In the next row, the arrows get longer as we go to the right. This would imply that the car is speeding up while moving to the right, or it might imply the car is slowing down if those arrows represent time. In the third row, the arrows get shorter as we move to the right, so this would imply the car is slowing down while moving to the right, assuming those arrows represent distances. This is why it's important to provide some type of way of interpreting your models so that there wouldn't be confusion on what they mean. Another way to model the motion of the car is to put a single arrow in front of the car to show its direction and speed. The arrows would have equal lengths, but the faster the car is going, the thicker you would draw the arrow. In the top row, the car is moving to the right, the arrows are staying identical, so that's a constant speed to the right. In the next set of drawings, the arrows get thicker as they move to the right, which would imply speeding up while moving to the right. And then if the arrows get thinner while moving to the right, the car would be slowing down. All of these are perfectly acceptable ways of modeling the motion of the car pictorially, and there are many other ways to do it. The simplest way to do it is to just use a series of dots in which the spacing of the dots is proportional to the speed of the object. We assume that going from one dot to the next takes the same amount of time, so that the farther apart the dots are, the faster the object had to be moving. Since a series of dots doesn't always let us know which end was the starting point, we'll sometimes put an arrow next to the dots to show the direction that we're moving. In these first 3 set of ticker tape drawings, the car is moving to the right, or the object is moving to the right at a constant speed because the dots are evenly spaced. In the next row, the dots get a little bit further apart as we go, so it's speeding up while moving to the right. In the third case, we see the dots get farther apart, but at a quicker rate than the ones right above. So it's also speeding up while moving to the right, but at a greater rate or acceleration than the one right above it. If we have evenly spaced dots, the farther apart the dots are, the faster that constant speed. So in our first row, we have a constant speed to the right. Right below it, we also have a constant speed to the left, but since they're closer together, that's a slower speed than the one right above it. If these dots below were half as far apart as the ones above, that would imply it was moving at half the speed of the one above it. Our final 3 show a constant speed that's greater than some of the other constant speeds we've seen. We see moving to the left, dots getting closer together, so that's slowing down while moving to the left. And then we see dots getting further apart as we move to the right, so that's speeding up while moving to the right. So out of all the different ways we can pictorially model the motion of an object, the dot diagram is generally considered to be the simplest way to do it.